So the shame is at the chemistry level we talk about, we can't really talk about practical applications because this is something that's truly covered at a higher level. But I do get students to ask the question, where does this come to practically? And I'll sometimes allude to the fact that engineers love using rate laws because the rate laws are useful for predicting reactions. So this is kind of an optional video to give you a perspective on how rate laws are actually applied in the real world. So in this first video, we're going to talk about what are called continuous stir tank reactors, or CSTRs. Now the idea with a CSTR is that you have a tank, and your tank is stirred mechanically or just by normal mixing. You have some reactant flowing in and some reactant flowing out. So your inlet flow, we're going to represent with this script V, and inlet concentration A0, some outlet concentration A, and some outlet flow. In this case, we're going to say it's V. So we're going to say the flow in equals the flow out. So what we have to account for is, well, what we want to know is what the concentration is coming out. This is actually a chemical engineering process. This is something that actually is done industrially. So we have three terms. We have the four terms. Accumulation equals in minus out plus generation minus consumption. So we're going to assume this reactor operates at steady state, so there's no accumulation of A in the reactor. The amount we have flowing in is little v times the starting concentration. So your molarity times your volume gives you moles. What we have flowing out, there's our flow rate times our final concentration. So this is in minus out. Now, if we didn't have a reaction going on, intuitively you could say that the starting concentration equals the outlet concentration because this term should be zero. But we know that we are losing some to the reaction. And so to account for the fact that we are losing some to the reaction, we've got this consumption term. We're not generating, but we are using some. And this is just set by the rate of reaction. Now the rate of reaction is molarity per unit time. And so what we have to do is multiply it by the volume of the reactor, big V, times R sub A. So in terms of your kinetic models, okay, this is where you'll see these R sub A start popping up, is when you start trying to figure out what's happening here inside this reactor. So if we factor out, we get 0 equals V A naught minus A minus VRA. We rearrange, we get our rate law A equals V over big V, starting concentration minus the final concentration, where this V over V is 1 over our residence time. Now, what we want to know from this reactor design is if we want a desired outlet concentration, let's say we're trying to get rid of some type of contaminant inside this reactor by reaction, we need to know what the expression for RA is. If it's K, 0 order, then we just figure out what the residence time is. In this case of A, we're going to have to rearrange to solve for A. If it's A squared and so forth, we have a lot of different forms. But whatever your form of the rate law is, this is the equation you're solving every single time to figure out either what the residence time is, which is dictated by your volumes of your reactor, your flow rates, or basically if you have a reactor of a given volume, different flow rates, starting concentration, what do you expect the outlet concentration to be? So this is one application of these kinetic models, or continuous stir tank reactors. If I have a reactor running a reaction, how fast do I need to flow it? How big does the reactor need to be? What do I expect the outlet concentrations to be?